Our aim was always a little bit different from what people have been doing, for instance, in the material side, the materials community. And the reason for that is that we wanted to take catalysis in a kind of holistic way. Okay, we didn't want to make differences between molecules and solids, and that's because of the people that was working in my institute that is working mostly with molecules, and molecules are an important part. And as you have seen, molecules have lots of spins and have lots of problems. So basically, we started very early on, so in 2015. And nowadays, our database has 7 nodes, about 500 users, and more than 600, I think it's more than 700 open collections. We have users from many different places in the world, which is very good for us, trying to get as many people as possible. So basically, the full idea was to collect all the information that was on a paper. So our idea is not to database materials, for instance, like in the material genome, but associate all the data that was related to one of the particular works, okay? And as an editor myself, I have found collections like 1,000 pages of this list. And of course, I didn't went through them myself because this is basically so error prone that it's basically useless. Okay, so ICIQ is mounted in this way. You can select the different types of outputs. There will be molecules or solids. And basically, we are extracting the information that we want and trying to put it together in the very same way. So this would be one of the examples, for instance, for one of the geometries of a material. Okay, and this comes always linked to the paper. So you can directly see both things, the material and the paper for each of the things that we have in there. Okay, you can also get different production out of it. So, for instance, data summary, different connectors to the DOIs, and different elements for data visualization. In the platform, the way we work is we have a private storage that can be completely blocked to people from outside, and only when the data becomes public, normally after some period of embargo, that we are taking it for the paper, if we are submitting a paper, and then when the paper is accepted, the embargo is lifted. And in this way, we typically, what we do is send the paper plus a link to reviewers that it's kind of a critical link to the reviewers. And the platform has these 3 units: the create, the browse, and the find. And basically, these are also linked to different tools and applications. So in the create part, this is kind of the private storage. You need to log in order to access and generate more data. You can serve by metadata, users, and groups. And you have different tools that allow the report generation. And there are a couple of services that are a REST API and a shell client. Okay, so this would be how the create module works and looks. Of course, we have added some different elements that can generate, you can see here, from reaction networks to reaction profiles to some experimental data and so on. Okay. Normally, what we do is we use different commands or files, convert the stuff, and get into the private storage. Okay, and this is completely tagged, so all the metadata is there, and you can really use it at this stage. You can generate these different reports, for instance, the reaction profiles that people like them so much, and adequate your system to different publications. You can request it as UI, publish the metadata, embargo, and all these functionalities. Similarly, in the browse part, this is public access. So you can check the DOIs, navigate all the different dataset collections that we are having. You can browse by terms and by different units. search some kind of metadata and check the syndication and do some data harvesting. In this case, there are several services and connectors also and different other functionalities. This is how the browse looks like. So these are the different groups, even my group here. And yeah, you might recognize some names maybe there. Yeah, in the browse part, well, basically we are trying to trace the different communities by the origin and also the name of the particular groups and the different authors. Okay, in each items, I mean, there is all these structures and all the important statistics, and we can also monitor the visiting statistics up to a point. Okay. You can also search and browse. We can really improve. We are really improving all these parts so that it's not so disconnected. And this is the part on the embargo. So typically people will see their data in this way. It will be under embargo, and when the embargo is lifted, you can start seeing all the different structures for the different systems here. Okay. Finally, in the find place, what we are getting is a distributed database. So we are getting all the information that is coming from the different nodes, that it's in a central node. This central node is supercomputer in Barcelona. So we have problems with having to store all the information ourselves. We are implementing advanced indexing of chemical data and metadata. And we have a fast search engine that it's implemented with some Apache Sol and Redshift frameworks. The searching mode is well, the find mode is a little bit it's being worked on it, because our idea is that we can find the same motive in different materials or compounds. Okay, so all the way not being forced by saying one thing in a solid. I mean, we want to be as transversal as possible. And this is why we are having this search by both the metadata and the chemical structure. So particularly the superstructure and the chemical structure for us, trying to see motifs that we can have in, for instance, organometallic chemistry that can be translated into heterogeneous catalysis. Okay. Yeah, in general, we try to have the data as linked as possible and as fair as possible. So examples that people has been using our structures and our codes. I will show you one here. So basically, this is how the platform is working with the central node that is sitting at the Barcelona Supercomputer Center. The local nodes that can be protected against or located. For instance, some companies have already installed IOChem for themselves, and they have their own calculations there. Okay, so yeah, basically these are the different nodes that we are having. And this is just one example. So a few years back, we published something and someone complained. And the reason why they complained is because they were able to download all the structures and check all the structures one by one. Okay, so one of the good things about making public audio databases is that someone took our simulations, rerun them, identified something that they thought that was affecting the outcome of the calculations, and basically they could rerun all the structures because all the structures were there. Okay, so they revised the setting. They suggested some approximations, so we did check. The sad thing for me is that they upload the results to Zenodo. So in a way, the fact that we had uploaded them with all the metadata ended up in another set of data that was uploaded, but in a place where you don't have the metadata, and recovering all the structures would be more difficult because there would be less reach in all the metadata and all this. Okay, so this ended up like this. We extended the simulations and the conclusions hold, so there was nothing happening really. So that was good. So I think that this is an important take-home message. It's important to have all the data there because someone else can come and take it from there, from the last place that you left it. But it's also important that if you have made the effort of generating all this data, metadata, and that it's available for everyone, at least the next one that comes shall do exactly the same. Yeah, and with this, I promise you that I was going to be very short. I want to thank my team, the team that is developing ICIQ. So we have a senior software engineer, a couple of people that is trying to develop this further, and trying even to generate equivalence for experimental data. In our case, experimental data in my center, it's a little bit more difficult because it mostly comes from homogeneous catalysis. But there is a part coming from homogeneous catalysis and then a part coming from solids. So the dispersity is very, very large. And this is going to be a huge effort. So we are not advancing that much there. With this, I will just close and thank you very much. I will take any questions.
Thank you for a really nice talk. So one of the big challenges in building open databases is to get users to upload data to your platform.
Yes.
So how do you ensure that uploading data is user-friendly, but at the same time you get enough metadata to make the data reproduced? Do you like have raw electronic structure output files?
So from the technical point of view, I mean, from the practical point of view, for us was a change of culture. I mean, we told the students of the 3 groups that are doing computation, okay, from today on, every paper that comes out from our labs, either is like this, we will not go unpublished. And it took a little bit, and also when you start thinking, I mean, this is, of course, dangerous if you are a small group sitting in a corner of the world, but you don't, you have a very good idea, you have your fears that something will go wrong. But it has paid off, at least for us. So we are really happy. From all the metadata, well, I mean, most of it is coming from the same scripts that are cleaning the files. Of course, if there is something new coming, you have to adapt those. So there is a lot of work that needs to be done, and this is why we keep the development team. And there should be another way to learn it from ontologies, from more general ontologies that can provide what are the important metadata for each of the systems. I know that there is an important effort in trying to merge all these different databases that have been around, have populated around. And I think that eventually we will get some good kind of rules of what needs to be there. But of course, I mean, if you're starting your calculations with a certain spin, and the spin is important for your system, that will be a problem. Yeah, but yeah.
What's the scale of data that y'all can handle? So I see, you have a couple hundred collections, a couple 100,000 data points. If someone came to you, is like, oh, I'm trying to publish a paper with a data set that has, 1 million materials, would you be able to handle that? Like, sort of, what's the?
I will squeeze my team to do that, but that's not the answer that you want. Yeah, we have enough space. I mean, we have enough space, and the platform is versatile enough. For one of the systems, I think we uploaded 50,000 calculations. So this we are doing as routine. So if there is something special that needs to be done, we could adapt. Of course, then the way of reporting here is very visual, and it will become useless. So having all this list. But with respect to space, I think that this is one of the things that we need to use also the supercomputer centers for, to store our things. Because I guess that many of you have the problem of what I do with this. And we have been extremely lucky and the supercomputer center in Barcelona it's very generous with us. I mean, we have enough space so that if we need to upload 1 million calculations, well, it's gonna be painful and someone is gonna complain, I guess, for a bit, but we will be able to do it because, I mean, space-wise, that's not a problem. And I know that at least the supercomputers in Europe are doing a lot of pressure in order to be the responsible for the data that is being generated. Okay, so in our case, until a couple of years back, medical data of high importance was trashed because there was no place where to upload it. So they really made an effort to make enough space for projects coming from outside.